All right. So just a few announcements to start. As you mentioned last week, so midterms going to be on October 16th, 7 to 9 p.m. Pacific time. And so if you have an exclusive conflict, please fill out this form as soon as possible so we can make the necessary accommodations for you. Homework 3 is out now. It's due this Thursday. As usual, turn it on Wednesday for bonus point. And vitamin 8's out, so I just complete that before Wednesday's lecture. So those are main announcements for today. And then in terms of kind of what we'll be doing this week, we'll be just wrapping up what we started last week in terms of visualization. So, last week, we did quite a lot of things actually last week. So, we talked about how do you make tables from scratch, how do we load a table into Python from a CSV, how do we select different columns, how do we manipulate the table, look at kind of subsets of the table, specific rows of the table, all of that. And then we finally started to also visualize data for the first time, which is pretty exciting. So we went over line plots, scatter plots, and then very briefly at the end touched on distributions. So today we'll go into more detail on what is a distribution, how do we visualize it. There's certain different ways that we're going to visualize it depending on what your data looks like. There's mainly 2 ways that we're going to focus on. So those are the main ones to kind of keep in mind. And there'll be some other kind of principles that are just really important for data science in general that we're going to go over today. But before we start, one thing I wanted to show you guys to keep in mind when you're making charts is always look at the y-axis. So the y-axis is like this axis here that goes up and down. And so this is a graph from several years ago when Bush was president, and basically they're showing on the news that if the tax cuts expire, then the tax rate for, I guess, the top portion of the country in terms of income was going to go from 35 to 39% or something like that. And so in this graph, they've started the y-axis at 34 and then ended at 42. So it just seems like it's this gigantic increase in the tax rate. But if you're being totally truthful, you should always start your y-axis at 0. So if you have anything numerical or percentage based, always start the y-axis at 0 and pay attention to that when you're looking at graphs. Because if you see here 35, 39, it is big, but it's not as big as what was implied here. So always be a little bit careful there. All right, so now on to distributions. So before we start looking at distributions, there's going to be some terminology we want to go over. So firstly, we're going to use this terminology called individuals. So that's essentially, you can think of them as people, but they don't have to people. So on Friday, we did an example where the individuals were movies, right? And so basically they're just kind of individual entities. And so that's going to be terminology that we're going to use constantly in data science. And then typically, there's also going to be one or more variables that we care about. And so a variable is kind of like a feature or an attribute about the individual. So in the case of the movies, we actually had several variables. We had what was the year that it came out? That's one variable about a movie. We had how much money it made, what studio made that movie, and so on. So this is going to be kind of the classical stuff that we're going to have always in this class. And in data science in general, you have several individuals, and then you view different variables about them. And typically the individuals are in the rows of a table. Typically the variables are going to be in the columns of the table. So that's kind of generally how we're going to see them. And then there's a lot of special things about these variables. This is the most interesting things for us. So first of all, typically variables will take on different values. That's why they're called variable. They wouldn't be that interesting if every individual had the same value, but variable probably isn't that interesting because everybody has the same value. So if you're looking at a survey of people in California and you have a column that says species or something, everyone's the same species, it's not that useful. So typically variables will have different values. In the case of age or the year that a movie came out, obviously, there's different years that it could have come out, so there's different values there. And then one thing to keep in mind for this course in particular is that these values can be either numerical or categorical. So numerical basically means that they take on some kind of numbered value, typically where the order has some meaning to it. So, the year 2007 versus 2012, clearly 2012 is greater than 2007. It's a larger number. So there's some kind of order there. Whereas in categorical, typically you have different categories where maybe there may not be an order. There can be categories that do have an order, which we won't really cover too much in this course, but in general, categorical just means like different categories where there may not exactly be an ordering. So, you know, for example, like if you have like colors, right? Like red and yellow, like is one greater than the other? Not really, they're just different categories. And so that's typically how we'll use categories. You know, gender is another common one that we'll use a lot. Let's see, in the case of the movies, you know, the studio that the movie was in, there's a lot of studios that could have made a movie, but at the end of the day, they're all just different categories. It's not a numerical variable. So that's another good example where you can have like a lot of categories for your categorical variable. Are years categorical? Typically years will be numerical, just because there is kind of a clear ordering there. So yeah, that's a good question. Ooh, this is a really good one. Someone said, are zip codes an example of a numerical thing? Technically, zip code is just like 5 numbers, but is it categorical? I think you could argue that's categorical, yeah, because those are basically just different categories. Like you can't really order the zip codes necessarily, unless there's like a particular way that you want to order that you care about, but typically you'd consider them categorical. So yeah. And then the other thing that is really important about the variable is that it takes on exactly one value for each individual. So if you're looking at a particular movie, it takes on exactly one year that it came out, or it takes on exactly one amount of money that it made. It can't take on multiple values. So that's also very important about the variables. And the last thing, which is kind of what's important for today, is that each variable has a distribution. And so what is a distribution? Well, distribution is essentially just you take each unique value of the variable and then just count up how many individuals have each of those unique values. So for example, if you were looking at movies and you wanted to look at like the distribution of the studios, for example, then you would just list out all the unique studios that there are and then just count up how many movies came from each studio. And so that's essentially just giving you distribution. That's what it is, what a distribution is. So just kind of list of unique values and then how many individuals have those unique values. So that's pretty much it. And so we'll kind of talk about distributions of 2 different types of variables today. So we talked about how there's categorical and numerical. We'll start with categorical because that's kind of what we already introduced in class on Friday. So we'll just kind of continue with that a little bit of a recap too. But yeah, so let's go to categorical distribution. I can make this a little bit bigger for you guys. So today we'll just kind of revisit that same data set that we were already looking at last time. So I'm going to call this top movies. And we're going to read in table.read table. And then there's this CSV file that has all of the data that we care about for these movies that were basically the top grossing movies every year up until 2017. So you can just kind of look at what this is again. So you can see here we have the name of the movie, which studio made it, what was kind of the gross earnings, gross adjusted for inflation, and then year that it came out. So these are kind of the main variables that we have for each of these individuals. And then what we want to do, let's say we want to look at the categorical distribution of just the studio. So we just want to see kind of, you know, how many movies are made by Paramount, or how many top movies are made by Paramount as opposed to Universal, as opposed to MGM. So we can actually do this. So firstly, what would be helpful is we can actually just, one way to do this is we could just take our table and then select just the studios column. So we can do top movies that select studio. Let's assign that to the name studios, and then we can just take a look at what that looks like. And so if you look here, we've just taken the column studio on its own. And so you can see MGM comes up once, then Fox comes up twice, then Universal, then Paramount twice, then Universal again. So you could really go down this and like count them all up if you wanted to. And that's kind of how you would create a distribution. So you kind of just go down this, count up how many times does MGM come up, how many times does, you know, each one come up. So you could do that. That's one way to do it, but probably not the most efficient way. Another way you can do it is using a new function that we haven't really talked about yet, but we'll go into more detail later in the week, is a group. So you can actually just take this entire column and just group the same values together. And that's essentially what group does. And it's going to also just count up how many times each of the unique values comes up. So we can actually do this as well. So we're going to call this studio distribution. And we're going to take this studios that we just made, which is the studios table with just one column selected. Which is our movies table with just one column selected. And then we'll group by studios. You have to specify which column you want to group by. In this case, we just have one column, so that's fine, but we're going to group by studio. And then we can take a look at what this function actually does. So if you run this now, we see that we have studio distribution is actually a new table that has two columns. So one column is called studio, which is the same column that we passed in here. That's kind of the column we wanted to group on. And then we have this new column called count. And so what the group has done for us is it's gone through the entire table and found the unique values, which are listed in this first column here, and then counted up how many times it shows up in the table. And so Buena Vista showed up 35 times. That's what this means. And so essentially, in our list of, I think there's around 200 movies, 35 of them were made by Buena Vista. So that's kind of what this is doing. And so I wouldn't worry too much about kind of how group works and how we used it yet. We're going to go into like all the specifics of it later. But this is kind of this is one way to actually create a distribution. So what you're seeing here is a distribution. What we saw above wasn't really a distribution. It was just listing out all the unique values. Or not all the unique values, but all of the movies. In this case, we're actually counting up how many times each of them showed up. So this actually is a distribution. It's literally just all the unique values, how often each one shows up. So this is going right to the definition that we just went over essentially. So just stop for a couple questions. Oh, that's a good question. Can you sort by descending order so that you could view like which one has it the most? So yeah, you should be able to do this. So we could do studio distribution.sort count. So if you just do this, this actually sorts it in ascending order, and then you could do descending equals true. And so now we've sorted this distribution with the count at the top. So yeah, that's a really great question. And this is typically something you want to do with distributions in general, because it's with categorical distributions. It's nice to be able to see kind of which one shows up the most, which one shows up the least. And so this is a really nice kind of intuitive way to look at it. That's kind of preferred actually to just looking at it alphabetically. Would this also work as one line? Yeah, sure, you could definitely do it as one line. So we can actually do that. So we could have just taken studios.group. So I can just put that down here, and then I can also take this sort function and just chain it all together in one line. So if you wanted, you could do this too, and you're gonna get the same result. But it's kind of nice to break things up into steps, makes the code a little bit easier to read. Sometimes you don't wanna have like so many functions on one line, just a little bit easier to read. Yeah, you could use operations on the original table as well if you wanted to, but we just kind of split it up. We had our original table of all the movies, then we created a new table called studios, which has the entire table, but only the studio column selected. And then we created yet another table called studio distribution, which took that studio table and grouped it. So it's kind of broke it up into 3 steps, but you could do it all in one line if you wanted to, actually. It just gets kind of long. It won't even like really fit on the screen here. So it's a little bit hard to read. All right, one more question I'll answer. Is it always create a column called count? It does. So the group function up here, it creates this count column for you automatically. So it's just always going to do that. And you can kind of expect that. At least that's the way that we're calling it right now. We'll go into some other ways to use this function later in the week. Cool, so that's basically how you can view a distribution of categorical variable. Just use group, and that will count up all the times each unique value comes up. Now, if you want to actually visualize this in a chart, a little bit different, but it's going to be the same kind of idea. So when you want to visualize this in a chart, we're usually going to use bar charts for categorical variables. And so with bar charts, you're going to have, like any other chart that we've seen so far, you're going to have 2 axes. So one axis is going to be kind of the categories, and another axis is going to be numerical, which is basically going to convey how many times that category comes up. And so we can just go through how to do this. We actually did this on Friday, but we'll just show it again. So if you have your data grouped, studio distribution, then you can just do bar H studio. And then this actually plots it in a bar chart. And so this is essentially kind of just graphically conveying what we saw in that table. So you know, remember it said Buena Vista had like 35 movies or something like that. So it's essentially just conveying that here visually. So this is a little bit easier to read, I would say, than looking at a bunch of numbers. That's just me personally. And then someone had said, you know, could you order this? Because it might be a little bit easier to read if it's ordered based on which one came first. So we can do that as well. We'll basically do what we just did above. So we'll do studio distribution dot sort, and we're going to sort by count, descending equals true, and then call bar H on that. And so if you call bar H on that, then we get the same chart, but now it's sorted. So it looks kind of nice, and it's really intuitive, really easy. You can figure out right away, okay, I know Buena Vista is the one that shows up the most. I know that, you know, these ones down here are the ones that show up the least. So very, very quick to kind of understand the main takeaway of what's going on in the distribution. And one thing that's interesting about categorical variables is that we were able to reorder this y-axis. So we were able to kind of change which category came before which one. And again, we could do that because the categories don't inherently have any sort of like ordering. Typically for numerical variables, that's not going to be the case. So if we're trying to visualize a distribution of numerical variables, we're not going to be able to just reorder things on the fly. There is a specific ordering that we're going to have to respect. And so we'll kind of go into how to actually visualize that in a second, but that's basically what it is. And then, yeah, sorry, let me scroll up to the code for how we did this. So yeah, just to recap, we had this studio distribution, which is a table of unique values and counts. And then we said, let's sort that table with count descending. So that means the highest count comes first, lowest count comes last. And then let's call bar H on that table, which will essentially visualize that for us as a bar chart. So bar H, actually, what does it mean? So bar is bar chart, H is horizontal. So that means it's like shooting out to the right rather than kind of shooting upwards. And so we did it horizontally here mainly because you could have a lot of categories. And so it might be a little bit easier to just kind of list them down this way, rather than if you did it like the other way, they'd be all squished together. And then you have to like rotate the text to fit like a bunch of categories, you know, along this axis. It's kind of hard to read. So horizontal is kind of preferred for bar charts for that reason, just a little bit easier. Another thing you might notice is that these bars are all equally wide, or I guess you could say equally tall. And the reason for that is so that it's really intuitive and easy to compare different categories. Because then all I need to do is look at the length of it, that's it. I don't need to worry about like, oh, one's thicker than the other and all that stuff. They're all the same thickness, but just look at which one's longer and you know that that category appears more common. So that's intentional in the way that this is done. And then how do you decide like how thick each bar is? That's kind of just aesthetic. So just depends on kind of how many different ones you want to have. And so, yeah, to clarify, studio is the vertical axis in this case. Also called the y-axis. And then count is what's on the x-axis or the horizontal axis. So that's kind of how you would say these. Cool. All right. So that's categorical variables. That's pretty much all we're going to do in terms of visualizing distributions for them. Bar H does like most of the work for us. And so we basically just saw two different ways to kind of view a distribution. You can view it in the form of a table. You can also view it in the form of a chart. And so it just depends on what use case you have. And so just kind of a quick recap of that. So distribution variable, once again, describes the frequencies of its different unique values. That's essentially what a distribution is. And in the group method that we just saw, is going to count up the number of rows for each value in the column for each of the unique values that the variable takes. So in our case, we saw the number of movies released by each studio. So that counted it for us. And then bar chart is what we use to kind of visually represent it. And so kind of key things there, you're going to see one bar per category, even though the category does appear multiple times in your data set, but you're just seeing one bar because we've kind of put all of them together into like how many times that unique value appears. And then the length of the bar is how many individuals are in that category. And as we saw, you can choose the order of the bars. You can kind of order things however you like. I personally like ordering it with that count descending. It looks really nice. It's really easy to kind of figure out what's going on. Cool. Can I show the last coding screen one last time? Yeah, sure. So just to recap this again, we had our table with different studios, how many times each one appears. Then we said, let's sort it by how many times they appear so that the one that appears the most is at the top. And then we said, let's visualize this in a bar chart. So these are kind of the main steps here. Okay, so now let's talk about numerical variables. A little bit more complicated. Some interesting differences here. So firstly, the biggest thing with numerical variables is that, if you didn't really visualize what it looks like, right? We talked about how at the end of the day, distribution is looking at the unique values and kind of the frequency of how many times each one comes up. But when you have something numerical, you may have each value only comes up one time because there's like infinitely many values, right? So if you're looking at, let's say, like a distribution of how much money the movie's made, right? Like one movie might have made like $10 million and 45 cents, and then like that's the only movie that made that amount, and they all make different amounts. So if you were to visualize it kind of in the same way, it would just look kind of weird because all the bars would just be the same height. It doesn't really make sense in the same context, just because you have infinitely many values. And so what we're going to do is something called binning, which makes it a little bit more intuitive for us to get a sense of kind of where most of these values actually are and how often they're coming up. So with numerical variables, we're going to bin them. And what that means is we're going to basically count the number of values that lie within specific ranges. So instead of looking at counting how many come up for a particular value, we're going to say how many come up within a particular range of this numerical variable. And so those kind of ranges, we're going to just call them bins. And so the way the bins are going to work is each bin is going to have a lower bound and an upper bound. And so the lower bound is going to be inclusive. I'll go over what that means in a second. And the upper bound is the lower bound of the next bin. So we'll see some examples of what this means. So for example, let's say that we had, we had a column of some numerical variable, and these are the values that it takes. Like 188, 170, 189, so on. And we want to bin these in some way. So one way we could make bins, and this is kind of up to you how you want to make them, but let's say one way we wanted to bin the data is like in increments of 5. So this first bin is going to be 160 to 165. Next bin will be 165 to 170, and so on. And so in the context of like lower bound, upper bound, what does that mean here? So basically 160 is the lower bound of the first bin, and then 165 is the upper bound of the first bin. And inclusive means that if you're trying to bin these values, essentially what we're going to do is we're going to take these values and assign them to a bin based on like which range they lie in. And the 160 is inclusive, meaning that if you have the value 160 exactly equal to 160, that should go in the 160 bin. But 165 is not inclusive. So if you have a value of 165, it's actually going to go into the next bin. The reason we do that is so that any value that's kind of on this edge between two bins has like, we know exactly where it should go. We have like a well-defined way of saying it should go here or it should go here. So basically, if you have anything that's like on the right edge, that's going to go into the next bin. And so that's basically what upper bound and lower bound means. That's what inclusive means for the lower bound. So 160 inclusive. So let's actually go through the process of putting these into different bins, one by one. So 188, that's going to go into this bin at the end, 185 to 190, because it's greater than or equal to 185, but it's less than 190. The next one, 170, that's going to go into the 170 to 175 bin, because 170 exactly equals 170, which is kind of the lower bound of this bin. So it wouldn't go into the previous bin, it would go into this bin. So that's kind of an example of that inclusive case. And then 189, that's going to go into this last bin once again. 163 goes into the first bin because 163 is greater than 160 but less than 165, and so on. And so one thing that you probably noticed here is that it called out this first bin as the 185 to 190 bin, and there's like a bracket on the left but a parentheses on the right. So this is typically just like in math how we denote that 185 is inclusive, like on the left side, but not inclusive on the right side. So this 190 with the parentheses is saying we go up to but not including 190. So it's like everything from 185 all the way up to but not including 190. So that's what that means. And so we can continue on in the same way. So I'll just ask you guys now to tell me. So 183, which bin does that go in? Yep, so 180 to 185, that's the bin it's going to go in. Then 171, where is that one going to go into? Yep, so 170 to 175 bin. And then 185, where does that one go to? Yep, 185 to 190. All right, so you guys are getting the hang of it, and so on. So 168 is going to go here, 173 is going to go here. And so now what we've done is, this is starting to look kind of like the bar chart that we saw, because we can actually see these kind of almost categories. You can see like different heights for them. Some of them have like bigger heights than others. And so that's kind of what it's nice about binning. Binning almost lets you kind of like convert your numerical data into categories in some way. And so it allows us to kind of just see the distribution a little bit more intuitively. And we can really get a sense now, kind of at a high level, we can kind of zoom out and see like, oh, okay, there's a lot of values from 170 to 175. There's no values from 175 to 180. So it kind of just gives you like a general sense of where a lot of the data lies for a numerical variable. And so this is kind of the principle we'll generally be using to visualize numerical values. And so let's actually now do a little demo of this. And so for our case, let's focus on the age of the movies. And so if you recall, this table of the movies actually doesn't have age in it. It has a column called year. So we want to look at the distribution of the ages. So if you want the ages, you have to first calculate the ages from the year. So we can do this. We'll do age. Let's make this new variable called ages, which is going to be 2020 minus top movies dot column year. So I'll just show it to you guys as well so you can see what it looks like. So this is an array right now. And this is basically just taking the year, subtract it from 2020, that gives you how old it is. And so we have it in this variable called ages, and let's add it back into the column and to the table as a new column. So we'll do top movies equals top movies, column, let's call this age, pass in ages, and then take a look at that. So now we have top movies, and we have this new column on the right here, age. So again, age, we just took 2020, subtracted the year. It gives us the age. All right, so now we have the ages. Now we're kind of ready to start thinking about visualizing this. And so before we want to visualize this, we need to come up with some bins. And so getting some questions like, how do you decide the size of the bins? It's really kind of up to you. It is a little bit arbitrary, but there are some reasons to do the bins in certain ways. A really common thing to do is just make all the bins equal size, but that doesn't actually have to be the case. You could actually make the bins kind of however you want. So let's actually try that. I'm going to just make some bins like however I want. And before you make bins for your data, it's good to just get a sense of what's the range of the overall data. Like what's the minimum value, what's the large value? Because you don't really care about making bins outside of those values. So we can look at what's the minimum age, what's the maximum age. So it looks like the minimum's 3, maximum's 99. So with that in mind, I'm going to try to make my bins from like 0 to 100, and then I don't really care too much about things less than 0. I don't care too much about things greater than 100. So I'm going to just go ahead and make some bins here. So again, this is pretty much arbitrary. But we'll just go through it anyway. So we're going to do 0 to 5, then 5 to 10, then we'll do 10 to 15, and then let's do like 15 to 25 just for fun, and then 25 to 40, and then 40 to 65, and then 65 to 100. So let's just kind of mix it up a little bit. And so these are gonna basically be my bins, and we're gonna make this an array, assign it to my bins. All right, so now that's in my bins. And then what we're gonna do is we're gonna actually try to look at our data in a table form with the counts for each of these bins. And so we're gonna use a new function called bins to do that. So we're gonna basically do top movies dot bin, and then we're gonna pass in two arguments. So one is which variable do we want to bin on? In this case, we're talking about age. And then what bins do we want to use? We want to use this variable that we just made called myBins. So we'll do bins equals myBins. And then let's assign this to another variable called bin data. So we just kind of have it there. And we can like access it easily. So here's bin data. And so here's what it shows us. So it creates this column for us automatically called bin, which kind of shows you where the bins are, the left and right edge, I guess, of each bin. And then you have another column called age count. So this is also made automatically for us. So they just took this age and then basically whichever variable we passed in here, and they just added count there for us. And so what does this mean? How do we read this? So this first row, it's saying that for ages 0 to 5, there were 12 movies. Then for ages 5 to 10, there were 18 movies. Then ages 10 to 15, there were 17 movies, and so on. So that's how you kind of read this. And at the end here, you have this 100 and a 0. All this is really doing is, we know that there's no movies greater than 100 here, but it's really just telling us that the end of this last bin is 100. Because if they didn't show this row, we wouldn't really know like where that last bin ended. So it's just showing that for kind of completeness. It's letting us know that, okay, 100 is kind of the end of the last bin. But really, it's really just these columns up here, or these rows up here that you care about. The last one actually doesn't matter that much, but it's just telling us that's where the bin ends. Okay, and so yeah, getting a lot of questions on like why did we do the bins all like unequal? So I'll answer that question hopefully in the next 10 minutes, but not right now. But one thing that would be nice is, what if I wanted to do bins that actually just like, you know, they're evenly like spaced and equal width and all that stuff. So you can do that as well. So we could just take this top movies.bin here, and instead of doing my bins, we could do a set of bins that are kind of more evenly spaced. So for example, we could use this function that we learned about, np.arange, and we can make a range from like 0 to 101 in increments of 25. And so, quick question here, what does this actually do? np.arange 0 to 101 and increments of 25. What does that actually return? Any thoughts? Yeah, nice. So 0, 25, 50, 75, 100. So it goes up to 100. So I can just show that here in case you want to see it. So this goes 0, 25, 50, 75, 100. All right. And so those are going to be our bins now. So let's put that as our bin. So now they're all like equal width, 25 width, and we can run this, and now we get something slightly different. So this distribution looked a little bit different now, but read this in the same way. So there's 88 movies that are 0 to 25 years old, 66 movies that are 25 to 50 years old, 38 movies that are 50 to 75 years old, and 8 movies that are 75 to 100 years old. So that's kind of another way to make the bins. And so this is what's interesting about numerical variables, is that technically there's many different distributions that you could have. You know, whereas with the categorical, there's like kind of only one way to really think about the distribution. But with numerical, it depends on which bins you use. The overall kind of shape of this is still about the same, and we'll kind of be able to visualize that in a second. But it's really just kind of, you do have slightly different ways that you could visualize this distribution and view it. So now that we've seen how to view this in table form, now let's finally figure out how do we actually look at this type of distribution visually? How do we actually create charts of this? And before we do that, we need to go over one really important, I guess, just principle about visualization. But before I do that, I do want to stop for a few questions. Why do we say bins equals instead of just passing in the array? A lot of times it's a good idea to specify like what the argument is, especially because there can be functions that have multiple arguments and some of them are optional, like you don't need to include them. So sometimes it's helpful, not just for Python to know this as well, but just for anybody reading it, like what that actually means. But yeah, in general, this is going to be a pattern that we're going to see a lot, where you're going to say, what is this, what is the name of this actual like input into this function? In this case, it's bins. That's kind of what the function is going to call this. Does the name of the column change from age to age count? So remember that what this is doing is this is creating a brand new table. So the top movies table is still the same. It still has that age column. But when you call topmovies.bin, this actually returns a new table. And that new table, it happens to have a column with the name age count. So this is kind of what bin does. It's always just going to do whatever you have here and then count. So instead of age, if you did like gross earnings, it would be like gross earnings count. So yeah, it just kind of does that for us. So will the last bin always have a count of 0? It should have a count of 0 if the range of your bins includes all the data. So in this case, you know, there was no value of age greater than 100. And so that's why it didn't say that there was anything like greater than 100 here. We could actually try to see what happens. Let's see what happens if we change this to like 75, or let me do 76 actually. So I'm just going to copy paste it down here. Just keep this one up here. So let's see what happens if you go from 0 up to 76. So you don't actually include everything that's in the data, because clearly there's movies that are between 75 and 100 years old. So if you forget to specify bins that go beyond 75, let's see what actually happens here. So again, np.area 0 to 76, and increments of 25 is going to give us 0, 25, 50, 75. So we actually look at that. And so if you look here, yeah, it does something a little bit strange. So like it has 88 in 0 to 25, it has 66 in 25 to 50, but then it puts 39 in 50 to 75. Instead of up here, we had 38. So it does something like a little bit stranger. But basically, you do still get 0 at for this kind of at the end here. So it's not really going to tell you like how many are left out or anything. It just kind of does it with context of like what you have specified. But basically, the idea is you should make your bins include make sure your bins include the entire range of your data. Yeah, I actually don't have a good answer for why that's a 39 instead of a 38. Maybe Yanai or Professor Wagner have a good answer. I'm sure there's a good reason for it. But yeah. 75 has a 0 now. Yeah, that's right. 75 has a 0 now. This doesn't mean that there's 0 variables or 0 values above 75, because we know from this one above that like clearly there's 8 values above 75. But it's just, this is how the bin function works. It's just always going to have the 0 at the end. And the 0 at the end is basically just letting you know that like that the 75 is kind of the end of the last bin. Okay. Cool. So now let's actually go into visualization. We just have a few minutes left, but we do want to cover this. And so first, we're going to talk about something really quickly called the area principle. So this is a general principle in visualization that's really good to keep in mind. It's going to be particularly important for visualizing numerical variables. And so this is for a picture from like several years ago when some new iPad was released. And the caption said, the new iPad battery is 100% bigger than the previous iPad. So 100% bigger basically means it's twice as big. But what looks wrong in this picture? Any thoughts? Yeah, everybody's saying it's not twice as big, right? Like, because if you look at this battery, right, if I was making something twice as big, maybe I'd just increase the width by 2, which is essentially what they've done here. But then they've also increased the height by 2 as well. So actually 4 of these batteries fit on the right here. So they're trying to like do some marketing and make it seem like this new iPad is like has a way bigger battery. But in reality, it's just twice as big. It should be twice as big. But in this visualization, it appears to be 4 times as big. So it's a little bit misleading. And so yeah, you guys basically all got it. And you know, this kind of goes to the area principle. So this is the principle that you should use when you're visualizing data. It's something that you should use when you're trying to like assess data. And you guys all kind of intuitively already did that, so that's great. And the idea is that the area that you show in a graph should be proportional to the values they represent. So for example, if you have 20% of the population as a triangle like this, then 40% could be represented with 2 triangles. But you shouldn't do a big triangle like this, because this is actually 4 times the small triangle. So this is misleading. So just kind of, you don't want to just look at the dimensions, like the width is twice as much or the height is twice as much. You have to just look at the entire area. I think this is somewhat intuitive. Like you guys saw it right away. Like, oh, that looks like way more than 2 times as big. But just good to keep in mind when you're making visualizations, when you're reporting things in the news. Just try to like be realistic about it and be truthful. So yeah, so that's the area principle, and that's going to be really important for us for visualizing numerical distributions. So we saw that categorical distributions are visualized using bar charts. The kind of corresponding graph for numerical variables is called a histogram. And so what is a histogram? Well, a histogram is a chart that displays the distribution of numerical variables. And it uses bins that we just talked about. And then the way it works is there's 1 bar corresponding to each bin. So it's going to look a lot like the visualization that we kind of created when we were assigning those different numbers to the bins in that slide earlier. That's essentially what a histogram is actually. And it uses the area principle. So the area of each bar represents the percent of individuals that is in that bin, or the percent of the data that's within that bin. That's what area does. That's kind of what it represents. So let's actually take a look at making a histogram. So we'll first do this with the arbitrary bins that I made. So if you remember, I had made this array of bins, and it was like 0 to 5, 5 to 10, but then it went from like 15 to 25, and then 25 to 40. So it's like kind of weird, but there's a reason that we're doing this. And then we also kind of put this together into a table which counted up how many values were in each of these bins. So we used the bin function to do that. And so that gave us this kind of a table. So it allowed us to kind of see this in a table form. Last step for us now is to actually visualize this in a chart form. And so how do we do that? Well, firstly, what might be useful is to actually figure out what percentage of data is going to go into each bin, because that's actually what's going to be visualized for us. You're not going to be visualizing the counts, you're going to actually be visualizing the percentage of data that goes into each bin. So let's actually just calculate that first. So if we want to know the percentage of data that goes into each of these bins, what we can do is we can do bin data dot column age count, and then divide this by the sum of the age count, which is 200. So there's 200 movies total. So we just take the count divided by 200 and then multiply it by 100. So that should give us the percentage of data that is in each of the bins. And so we can take this, let's just add this to our, actually let's just first look at it. So what this is saying is that the first bin has, oh, actually, I don't know if this is, oh yeah, so this is saying the first bin has 6% of the data. The second bin from 5 to 10 has 9% of the data. And then the third bin from 10 to 15 has 8.5% of the data, and so on. So we divided by 200 because we wanted the sum of all the values. So we wanted to know how many movies there are total. So there's 200 movies total, and we want to just figure out what's the percentage for each of these bins. So we know there's 12 movies in the 0 to 5 bin. Therefore, the percentage of movies that's in the 0 to 5 bin is 12 divided by the total, which is 200. So 12 divided by 200, and then we just multiply by 100 to kind of get the percentage in, without like decimal places, essentially. So now we have the percentage that's in each bin, and then we can just add this to this table so we can kind of visualize it all together. So we'll do bin data equals bin data with the column, and we'll call this %, and we're just going to pass in this thing that we just created above. So now we're going to add this to bin data as its own column, and then once we look at all this together, it'll make a little bit more sense. So basically what this is saying now is from 0 to 5, there's 12 movies. That's 6% of all the movies. From 5 to 10, there's 18 movies. That's 9% of all the movies. From 10 to 15, there's 17 movies. That's 8.5% of all the movies, and so on. And so 200 is the number of movies. It's basically the sum of this column here, the age count. So if you sum up the age count, you're going to get 200, because it's 200 movies total. Because again, this column is just telling us how many movies are in each of these bins. So we have all of our movies here. We've just kind of said how many go into each of these bins, like how do they split up. But the sum of that gives us all the movies. So now we have that. The reason I did that was it's really helpful to see that when we visualize now the histogram itself. So finally, after much delay, here's actually how you visualize this. So we do top movies, and we're going to use a new function called hist. So that's what we use to visualize a histogram. And we're going to first specify which column do we want to view the histogram of. In this case, we're talking about age. And then you have to specify which bins you want to use. So we'll use, for now, let's just use my bins, which is that kind of like weird set of bins that I made. And then you also specify the unit. I'll go over in a second what that is. But this is how you call the function. So just take your table and then call a hist on it. Specify which column you want the histogram of, which bins you want. And so now if we run this, we finally visualized a numerical variable, the distribution of a numerical variable. And so what we specify in unit here, it just puts it here in parentheses on the bottom. So this is saying that on the x-axis we have age, it's in units of years. And then on the y-axis, we have this thing that says % per year. And then basically, as we just said, the area of each of these bins tells you the % of data that's there. And so the reason that's important is because even though these bins are different, we have bins over here, the first 3 bins only have a width of 5, but then we have a bin here that has like a width of 15. But we can still kind of compare these because we can look at the area. And that's kind of why we did that, because you are going to see graphs like this in the future. Histograms don't always have this kind of uniform set of binning. And in general, the most important thing is really the area. That's really what you care about. And like looking at different ranges of the data and understanding how much area is there versus in other parts. And so this makes it a little bit easier to kind of compare which bin has more data. So that's kind of how that works. And that's how we visualize a histogram of numerical variables. And we could also just not specify any bins if we wanted to. So we could just do top movies at hist, age, unit, year, and just run that. And what will happen then is Python's going to use its own bins. So it just makes up bins for you. One problem with this is that you don't really know where the bins begin and end. So for example, like this bin here, it's like starting at maybe, I don't know, like a little bit past 30, and then it ends a little bit past 40, but I don't really know exactly where it ends. So you kind of don't really have control over like where the bins start and end. You don't actually even know what they are. So it's a little bit better to just kind of specify your own bins typically. And then we could do the bins that we actually tried before, where we said np.arange 0 to 101, commits to 25. We could try that one as well. And then this is how that looks like visually. So you can kind of see that as well. And so now we have 4 bins, each with width of 25. And does that mean the histogram should add up to 100%? Yeah, that's right. So all the area and the histogram should add up to 100%, because that's all the data. I mean, assuming that you're actually showing the range of all of your data. So yeah, so that's histograms. We're a little bit, it's basically out of time there. So I think what I'll do is we'll go over what does this mean, this y-axis, percent per year, first thing in the next lecture. So we'll just start with that in the next lecture. So don't worry too much about what this means yet, but we'll go over that. But yeah, this is basically how you visualize a histogram or distribution of numerical variables. And yeah, I'll stay for some questions as well.